Hey YouTube, what's going on? Welcome to the pick of the week. That's the math with Daniel Doe, sometimes combined with physics, as in this case. I made a specific selection for you guys. That's differential equations, and this is applied math for fluid dynamics. Recently, I found a problem dedicated to force and viscosity, how they are dependent on. I'm not interested about what I need to find there, but I decided to explore how the force of viscosity might be dependent on speed. In this case, there might be two types of dependency. Of course, there might be more, but the first is the linear one, as you can see here, and that's going to be quadratic one. So we hold on the linear dependency first, and then we keep going with quadratic dependency. But you might ask, what about differential equations? Definitely, that can be the case where you can apply your math skills in differential or in differentiation. So in order to solve some interesting problem like this, in our case, what I'm going to do, I'm going to show you first a free body diagram, and from there we can complete the equation from the second Newton's law. Okay, so let's describe that some object with a mass m is, let's say, it's sinking in the liquid due to the gravity force. So that's why if we start drawing free body diagram, we need to signify this is gravity force, mg, and what is actually opposed to it is the force of viscosity. So normally you know that force of friction force is not dependent on velocity, right? So, but in a viscous medium, like in fluid and liquids, when the body is moving in, so that's definitely the case when when the force of friction will be dependent on velocity, as in this case. So we put this friction force opposed to mg, and it was set up the second Newton's law that the resultant force actually mg minus f of friction force is going to be this way in the case when mg, gravity force, let's say, is greater than f. Let's assume that for simplicity. So what we can do, we can put the magnitude of f in this case and complete the equation where we can set up the acceleration and express it through the speed. All right, so v is the speed, I acceleration. But you ask me, where is the differential equation? So no problem, we can go back to definition of the acceleration, and we can set up the acceleration dv over dt. So that's why we'll get the complete differential equation with respect to the variable here is the velocity or the speed if we don't consider the vector way. Okay, so that's the differential equation, and normally we can consider using like dots. If you like, I can rewrite in this notation as well. So but I prefer in this case d over dt. So now you can see this is differential equation of the first order for velocity or for the speed. Let's try to solve that. So m and k, they are constant defined by a given problem. So you can set up as any. Let's assume that initial velocity, so initial velocity is going to be 0. It starts sinking, okay? And right now, what we're going to do, we are going to integrate, right? But first, in order to solve this differential equation, we need to split variables. Let's put that and say that dv over mg minus kv, that's the way how we can split variables. And we need to split or put apart dt, another variable of integration. So I write in this way, okay? So I divide by m and multiply by dt. Now we can integrate. Let's integrate that from, let's say, time 0 to given instance of time. And what about velocity or speed? From 0 to some v, current velocity. Okay, so that's how we actually resolve or trying to resolve this differential equation. Okay, so let's start doing, and let's say that in the case when we have v, that's the variable of integration, we need to input new variable and let it be the whole denominator, mg minus kv to be u, new variable of integration. Okay, so let's differentiate that and say that du actually is negative k dv because mg is the constant of integration. So from where we can express that dv is simply minus du over k. And let's put it back into our differential equation, all right? So what we're going to do, we are going to say that we will have du over mg minus kv becomes simply u. And here is new variable, new constant, minus 1 over k. So minus 1 over k before. On the right side, we can already integrate and we'll get t over m. So that's done. And what we're going to do, we can say that integral du over u will give us ln u in this case. Okay, yes, definitely. But u will change in the integration boundaries. But I don't care about that because we can come back to v from u and put new integration variables that was previous for v. So that's why, okay, we put some u0 to u, u0 to u. And now if we're coming back to our variable of integration, we need to set up ln of the variable mg minus kv now, and we're setting up the boundary of integration v and 0. Now it works properly. Okay, on the right side, we'll set up t over tk over m. Perfect. So what we're going to do right now, we're going to set up the boundaries and say that we have ln, so mg minus kv. We set up the top boundary and we subtract ln when we put 0, so we'll have ln of mg. So that's what we have on the right side, tk over m with a negative sign. Okay, so using the property of logs, we simply need to say that it's going to be mg minus kv over mg, and on the right side we'll still have that. It's not changing. All right, so let's move next. Here, what we're going to do, we're going to use e and raise to the power. So that's why we'll get mg minus kv. On the right side, we multiply by mg and we raise power negative t k over m, okay? Using the basic properties how to go from log equation into index form. And right now, what we're going to say that if we express v from there, we will have mg 1 minus e negative t k over m, all right? And that's going to be the function of v. So we transfer v to the right side, and that's why we need to divide simply by k. So if you like, we can divide everything by k, and that is going to be our v from time, okay? So that's the final solution for those differential equations that we had before. So now I'm going to zoom back and let's have a look briefly what we've done. So we actually found a solution in terms of v, how velocity depending on time, or how v depending in which way the speed depending on time. So we found that. Actually, right now we know how the force is depending on time as well, okay? And if we set up the graph, let's show it graphically. So what we actually got in this way. Oh, that's too bold for our case. Okay, so let's set up the xy set. In this case, it's not xy, but it's going to be v from time, okay? How speed depending on time. And we know that when t0, simply when t0, we will have, if t0, we'll get 1 minus 1. So that's why initial speed is going to be 0. That what we start from our assumption that initial speed is going to be 0. All right, so what we're going to do now, we're going to say that, okay, we have the terminal velocity when time tends to infinity. And indeed, your exponent, e negative t k over m, will tend to 0 in this case. So that's the starting point right now. And we have also the ending point when t is very close to infinity, means the very infinite time lapsed. So that means we can indicate with a straight line with the equation mg over k. Simply just plug infinity there and say that e to the negative tk over m will actually be very negligible. So that means the behavior of the speed v from time, and that straight line that goes through mg over k indicate that this is going to be the terminal velocity. So terminal velocity or terminal speed, and that means your curve of the equation v from time will have this terminal straight line, horizontal straight line, as the asymptote. Okay, so I hope you understand how it works. Okay, and the second stage is to investigate how force depending on v in different way. Let's have a look there. So the force is dependent on v as v squared. So let's take, let's say, absolute value, and we investigate as k times v squared, okay? Or let's put another, instead of k, let's put another variable or a constant. Let's say that negative k is going to be positive, let's say a, okay? It's not acceleration, just some constant. It's going to be a times v squared, okay? So on top of that, we can say that this is the friction force, right? And in the simplest case, let's assume that's the only force acting on the body. So that's why it will cause acceleration. Maybe it's better to say that, oh, sorry, my bad. Maybe put instead of acceleration, the capital A. So that stands for acceleration. And on the right side, we'll have AV squared. If we rewrite this equation in the way a over mv squared, we'll definitely know that acceleration is dv over dt. So that's why we'll get the following. So a over mv squared, okay, v squared. And now let's set up the question. We want to find how, let's say, the coordinate x or position vector r depending on time. So that's why we just remember that v is dr dt, and we can set up the following differential equation. So d2r dt squared is going to be equal to some coefficient a over m. Let's set up a over m as the coefficient, let's say b. All right, so we'll get b times dv. So that's, sorry, dr dt squared. Okay, so what we have a second derivative. In other words, we can rewrite using dots notation or prime notation. So the second derivative of r is going to be b, the first derivative of r squared. If you're wondering how to solve this sort of differential equation, that's the clue. So that's already, we got it from physics. All right, now we are going to solve that. Let's move on, okay, and let's try to solve it quick. So what we're going to use? We're going to use the fact that we already solved on the previous case. We solved the first order differential equation, and we can say that if we come back and say that dr dt is going to be v, right? So we'll get the following: dv over dt is going to be b v squared. All right, so let's split the variables, and right now what we are going to have, dv over v squared is going to be b dt. All right, that's pretty simple right now. We can integrate that, and if we integrate, we'll get the following: minus 1 over v, that's the left hand side, okay, and the right hand side is going to be bt, let's say, plus c. We are not going to consider trivial solution for v equals 0, of course. That works, that definitely works, and it works for r equals 0 as well, if you like that. Or not r equals 0, but probably r equal to some constant. Okay, that's actually going to be the initial position vector. Yeah, that would be more correct. But this is trivial solution, all right? So trivial solution. We're not going to consider that, and we want to be focused on that general solution right now. Okay, so what we can do the following. So we can express v from time and come back to dr dt. So right now we'll get dr dt is going to be equal, we just swap them, we can say it's going to be minus 1 over bt plus c, all right? And from there, we can again split the variables and integrate. So we can write dr is going to be minus dt over bt plus c. Okay, I hope you know how to integrate this sort of expression. That on the left side, we'll get r plus constant c, okay, c1, let's say, that will be equal to dt over bt plus c. Maybe, let's say, r be equal, let's transfer constant c to the right side. Okay, so in this case, we can integrate in the way if we're consider that. So d, instead of the old variable t, we can put actually new variable, but I just put the whole expression what I see in denominator. Okay, however, I need to make a correction here, because if I differentiate that, the b will be the constant, right? So that's why I need to divide by b as well. And in the bottom part, I'll have bt plus c. If you like this way of integration, because it works pretty fast, so please guys try to use that. It works pretty fast. Okay, and we'll get the following. So we'll get negative 1 over b ln natural logarithm for bt plus c in this way. Okay, so that's why it's going to be bt plus c. Okay, so it's done with that, and what we're gonna do right now, we're gonna say that right now we have the idea of how r dependent on time, but we need to add constant of integration, and instead of c, we can consider also negative 1 over b ln some constant, you know, c if you like that. Okay, so in this case, we can fix the problem and say that actually we'll have the following. If you like b, I'm not sure that we can use as the power. I don't recommend, at least. So let's leave 1 over b as the coefficient there. And we can say that it's going to be 1 over b. And we add in the constant in this way. So it's going to be ln of bt plus c. And because we add in logs, right, we will have times another c1. All right, so that's how it will look like. Okay, so we've got how their position vector depending on time, and it depending on time in the logarithm way. Okay, so that's an idea. This is the way how you can use apply mass in order to probably apply to different problems, real life problems, or problems from another areas that requires definitely differential equations. Hope you like that. Hope you clarify a bit more about fluid dynamics, how it works, and also make sure you can solve this trivial case when we have linear dependency, and also make sure you understand how to solve the second order differential equation. So I try to combine two in ones. Hope you like that. Don't forget to subscribe if you're new here. That was Daniel Dallas, and see you next time.